Let's continue with the questions which are in the first draw sheet for CBO, draw sheet 1. Question number 6. Analysis shows that 20 milliliters of concentrated hydrochloric acid of density 1.18 grams per milliliter contains 8.36 grams of hydrochloric acid. So you have got concentrated hydrochloric acid. And when you get 20 millimeters, you get to find that the mass in there is 8.36 grams. Now I want to calculate the mass of hydrochloric acid per milliliter. So how do you find mass per milliliter? So that means you have to divide the the mass by the milliliters for to find mass per milliliter. So the mass that you have is 8.36 grams divided by the volume, which is 20 milliliters. And then that will give you the mass per milliliter. So let's just get to do that. 8.36 divided by 20. This is giving me 0.419 grams per milliliter. So this is the mass per milliliter. And then the next one, calculate the percentage by mass of hydrochloric acid in the concentrated acid. We want to calculate the percentage by mass of the hydrochloric acid in the concentrated acid. Now, if you get to see from what we have, actually the one which is present from the 20 milliliters that we have, we only have 0.419 grams per milliliter. But from the density, we are supposed to have 1.18 grams per milliliter. So to find the percentage of hydrochloric acid, that would be what we have, the 0.419 grams per milliliter, divided by what we are supposed to have, the 1.18 grams per milliliter, and then multiply that by 100%. So that is 0.419, we get to divide by 1.18, and then we multiply by 100%. So this is giving us 35.5% of hydrochloric acid. So that is it for this question. Question number 7. What is the specific gravity of a liquid if 225 cubic centimeters of the liquid has the same mass as 396 cubic centimeters of water? Now, we know that for a substance, it has got the same mass as the 396 cubic centimeters of water. We know that when you're talking about water, of course, the density of water is 1 gram per cubic centimeter, like that. Meaning that if this liquid has got the same mass as this volume of water, what will be the volume of water with this mass? So since water has got a density of 1 gram per cubic centimeter, meaning that if the volume is 396, also the mass of water is going to be 396 grams. So meaning that this is the mass of this liquid that has been given. So you can actually determine its density. So its density is going to be mass over volume, and the mass is 396 grams divided by the volume, which is 225 cubic centimeters. So just get to divide 396 over 225. That is going to give us 1.75 grams per cubic centimeters. Now, when you're talking about specific gravity is the same as relative density. So specific gravity is the density of an object compared to the density of water. So the object has got a density of 1.75 grams per cubic centimeter. Divide that by the density of water, which is 1 gram per cubic centimeter. And so this will just give us 1.75 as the specific gravity. So question number 8. Cesium atoms are the largest naturally occurring atoms. Each has a radius of 2.62 angstrom. How many atoms of cesium would have to be laid side by side to a row of cesium atoms 0.1 centimeters long, assuming the atoms are spherical. So from here, what data do we have? So we have got cesium atoms, of course. They've got a radius of 2.65 angstrom, meaning that they are circular in this case, circular like that. Now, when you're talking about the angstrom, we know that 1 meter is 10 to the power positive 10 angstrom. So this is what we need to take note of. Okay. So from here, you are talking about how many atoms of cesium you have to lay side by side to a row of cesium atom 0.1 centimeters long. So I've got a row like this, okay, just like that, which is zero point 0.1. That's the distance 0.1 centimeters long. So how many atoms are going to be able to fit in here? So how are we able to do that? So we know that if we want to do that, in other words, we want to put atoms in this way, like this, in a row, like that, and they should give us zero point 0.1. How many of them are we supposed to fit for them to give us zero point 0.1 centimeters? So the first thing that we have to do is we need to convert the angstrom given, which is the radius of cesium atoms, into meters. We know that 1 meter is equal to 10 to the power positive 10 angstrom, meaning that if you are talking about the 2.6, let me just get to refer again to the conversion factor. Perhaps half is supposed to be 1 angstrom being equal to 10 to the power positive 10. Alright, so 1 angstrom is actually equal to, so just like I said. So it's supposed to be 1 angstrom being equal to 10 to the power 10 meters. So if it is 1 meter, it is supposed to be 10 to the power negative 10 angstrom. So we are now having 2.62 angstrom. How many meters are we going to have in that? So to find x, this is going to be 2.62 divided by 10 to the power negative 10. So that is how we are able to find that one, since we are doing a cross multiplication. Okay, so if I get to take this value on top, this will just give us 2.62 multiplied by 10 to the power positive 10 meters. So this is what we have. Now this value that you've been given for the row of cesium is in centimeters. So we also need to convert that to meters. We know that in 1 meter we have got 100 centimeters. So how many meters are going to be in 0.1 centimeters? So to find x, to simply be 0.1 divided by 100. And that is going to give us 0.001 in meters. So I have found the radius of cesium. We need to find how many of those atoms. So if we have found the radius, remember how we are supposed to fit these atoms side by side. We're supposed to fit them like this. And we want to count how many of these atoms are supposed to fit in this amount. So if this is the radius that we have, we need to know the distance from one end of cesium to the other end. That's the diameter. So diameter is given by 2 times the radius. So this is going to be 2 multiplied by the radius, which is 2.62 multiplied by 10 to the power positive 10 meters. Right, so this is going to give us what? So let's get to do that. And by the way, I've just gotten to check again The first one which I wrote for the angstrom was just okay. So angstrom is 10 to the power negative 10. 1 angstrom is 10 to the power negative 10 meters, meaning that 1 meter is 10 to the power positive 10 angstrom. Sorry for that again. So meaning that this value is supposed to be positive here, so is to give us a negative power, and that's supposed to make sense, right? So we are multiplying the 2.62 by 2, and that is going to give us 5.24 multiplied by 10 to the power negative 10 meters. So this is the diameter of the each atom of cesium. And so we want to pair up these each of this distance such that it is going to give us this one. So in other words, what we are just saying is how many times can this number go into 0.01? So all we are going to do is we're going to write the 5.24 multiplied by 10 to the power negative 10. Okay, so we're going to say 0.001 divided by that value. That is how many times can this number go into this. That will give us the number of cesium atoms that are supposed to go in there, because, or we can say, if one, this is one cesium atom, that's the distance that it gets to give us. So one cesium atom is equal to this value. How many are going to be able to give us this value? That is what we want to find. And then we do that operation. So that is going to give us a value of 1.908 times 10. Let me just check this. 1, 2, 3, 4, 5, 6. So this is to the power 6 atoms. So these are the atoms that have to be laid in a row for you to be able to get this bar which we have here of cesium. Now, since we are talking about a number, we want the number of atoms. Number can't be a decimal. So we could have given it as an order of magnitude, since it gave us 1.908 times 10 to the power 6. So as an order of magnitude, this can just be written as, we can get to round off this, so big 2 times 10 to the power 6. Now this is not an order of magnitude. So as an order of magnitude, you just get this which is here. So which is approximately 10 to the power 6. So in other words, you are going to use a million atoms to be able to fit in here, because when you are counting, you don't have decimals. Decimals just comes in when you're talking about measurement. Question number 9. The proton is thought to have a radius of 1.30 times 10 to the power negative 13 centimeters and mass of 1.67 times 10 to the power negative 12 grams. Determine its density assuming it is spherical. We know that density is given by mass over volume, right? So this is a sphere. We need to find volume first of a sphere. And what is the equation that we get to use to find the volume of a sphere? So the volume of a sphere is given as 4 over 3 pi r cubed. So this is going to be 4 divided by 3. We know what the value for pi is. And then the radius. So we've already been told that this is the radius. Now the radius has been given in centimeters. So we need to convert that to meters. We know that in 1 meter we have got 100 centimeters. So x is going to be equal to 1.30 times 10 to the power negative 13. So to find the value of x, simply divide the 1.30 times 10 to the power negative 13 by 100. We know that 100 is the same as 10 to the power positive 2. Now these are same bases which are dividing. Simply subtract the powers. So this is going to be 1.30 times 10 negative 13 minus 2. That will be negative 15. Okay, so that will be 1.30 times 10 to the power negative 15. I'll just get to say 1.3 multiplied by 4, then divided by 3. So that is giving us, I can go on and get to multiply by pi. So that is giving us about 5.445 times 10 to the power negative 15 meters cubed. So that is the volume. Now I've already been given the mass. Actually, I could have used this same value since mass is also given in grams. Can express density as gram per cubic centimeter. So I use this one if you are using the mass in kg. Okay. So we're going to say volume just the same 4 over 3 multiplied by pi, and then the radius is 1.30 times 10 to the power negative 13. So 1.30 multiplied by 4 divided by 3 just the same. It is going to be, and then we multiply that by pi to now be 5.445 times 10 to the power negative 13. So the mass is 1.67 multiplied by 10 to the power negative 12 grams divided by the volume, which is 5.445 multiplied by 10 to the power negative 13, which is in cubic centimeters. So here we have got the 10 to the power negative 12 on top and then 10 to the power negative 13 down. So when you are dividing, subtract the power. So 10 to the power negative 12 minus negative 13. So this will give us 10 to the power positive 1. So I mean that I'll just get to do the division of 1.67 divided by 5.445. Then the answer that I get, I multiply by a 10 which remained, which is this one here. So this is going to give us a density of 3.067 grams per cubic centimeter. So that is going to be the density. Okay. Indicate the number of protons, neutrons, and electrons in each of the following. When you get to look at this one, which is here, starting with the number of protons, the proton number is 15. That will be equal to the number of electrons, which is 15 for a neutral atom. Then the number of neutrons is simply the mass number minus the atomic number. So that is going to be 31 minus 15, which is 15 also. So that is for the first one. The second one, the number of protons also is 92. That will be the same as the number of electrons, 92. And the number of neutrons, it will be 236 minus 92. And that is 144. So that is it for that one. Then we go to the next one. The number of protons for this one is 12 as seen from the proton number. And then the number of electrons. Now we can see a charge of positive 2, meaning that you have lost 2 electrons. So instead of it being 12, it will now be 10 electrons from the number of protons. Then the number of neutrons is simply mass number minus proton number. So that will be 25 minus the number of protons, which is 12, and that is a 13. All right, so we are now on the next question. Question number 11. And question number 11 is telling us to get to sketch the mass spectrometer and discuss the importance of the main components. Sketch the mass spectrometer and also discuss the important components. Okay. Now, when we are talking about the mass spectrometer, well, it is not that, it's not a complex instrument really when you are discussing it. So since we just want to give a sketch of this instrument, what I'm going to do is I'll just make a very simple sketch. Right. and I want to make sure that I use a very simple one which is not complicated in any way. So let me see which one I'm able to use, which is going to be very much simple. All right, so the sketch that we're going to make for math, the mass spectrometer, what we have is we have got something like this. We have got something that is going to go like this. So at one point we have this thing is going to be able to turn, okay, like that. So at one end we have got the source of ions. At this end here, we're going to have the source of ions, and so I can write that, which is the ion source. So when these ions get to move in this medium, we have got a magnet somewhere here, and the aim of the magnet is to get to deflect ions. You know that ions are deflected by magnets because they are charged, so that's why they are going to be deflected by these magnets. Okay, so now what are the many components, and basically what we want to get to discuss here is specifically the ion source analyzer and also the detector. So at this point, of course, I've already shown the magnet. One part is going to be negative, the other part of the magnet is going to be positive, like that. We are going to have a magnetic field that is going to be caused by the magnet. At the end, we are going to have the detector at this very end here. Okay, we are going to have the detector there. And then at some point on the middle here, we are going to have the accelerator, which gets to accelerate ions. We are going to have just something like this, where ions are going to be accelerated on that region. Okay. We also have more a vaporizer at the beginning, like those are some of the parts. Now I want something that is very simple for us to discuss, that we just get to show the analyzer and also the detector. So we've already seen the detector from here. Okay. So now what is the function of the analyzer and also what is the function of the detector? Let me just get the analyzer from here. So remember we have got a source. Now let me enlarge this. Remember we have got a source of ions, but at the beginning, the source of ion, you just have more like one beam of ions that is coming, but at the end, you are going to have a lot of ions that are going to be seen. Okay, I hope this is just okay. At the end, you already seen that is where we get to have a detector at the very end. And then at the beginning here, we have got a sample or the ion source, which we said. So this is the one which is providing ion, that is a sample. Now at the beginning, we have got a neutral molecule that is going to be released. So as this neutral molecule gets to go, it is going to find a very small space here, a very small space where it is supposed to pass. So this is called a repeller plate. Here is a repeller where the neutron molecule has to pass from the source of the sample. We are going to have the electron beam, and then at some point we are going to have the accelerator, and there are more like two of them. These are spaces, the accelerators. So this beam is going to pass like that. When it gets to reach at this point, especially on the corner, this is where we have got now the magnets. So it's going to reach the magnetic field. We have got a magnetic field where we have got a magnet here. So what happens when it reaches there is that they are going to start deflecting. They'll start deflecting like that. So they'll deflect into different ions. Remember at the beginning you only have a neutron molecule, but you start deflecting into different ions like that. At this point, this is where we have got the analyzer tube. Okay. So what you have here is you have got positively charged ions. Now, the ions are going to be deflected in a certain order, right? In a certain order. Now, let's get to consider. We have got the analyzer and also the detector. That is for this question which we are interested in. So, what are the functions of the analyzer and also the detector? So, the first thing is that the ionizer. Okay, let me see. Okay, we also have got the ionizer that gets to form ions. So the ionizer is going to convert some of the sample into ions. We're going to have the ionizer, and then we're going to have the mass analyzer. What's the function of the mass analyzer? The mass analyzer separates the ions according to their masses, mass to charge ratio actually. Because what you are going to be able to see here is that you are going to have the mass to charge ratio. Okay, so the biggest mass to charge ratio is going to be a little bit deflected, and then the smallest mass to charge ratio is going to be the most deflected. So let's say this compound has got a mass of 10 and then a charge of 1, and then I've got another compound with a mass of 10 and then a charge of 2. So this one, the ratio is small, meaning that it is going to be deflected just a bit, is going to be on top. This one, the ratio is big, so it's going to be deflected all the more, it is going to be down. You have got the detector. The detector is going to record either the charge induced or the current produced when an ion passes by or hits the surface. So what is going to be the charge that is going to be induced when the ion gets to hit a surface? So that will be the function of the detector at the end to record that, okay, or the charge that is going to be induced. So that is what gets to happen. 12. Discuss how the field effects and particle effects affects the separation of ions in a mass spectrometer. Okay, the field effect and also the particle effect affects the separation of ions. So what is going to happen when the magnetic field is weaker and stronger? So expect that when the magnetic field is weaker, the ions will not be able to separate more, right? All right, and when the magnetic field is much stronger, you expect them to separate all the more. And when you're talking about the particles themselves, so if you have got particles which are more of the same mass, it will be very difficult for you to get to separate them. Okay, especially if they also have the same charge, because if you have got, let's say you have got potassium ion and some other ion X which has got the same mass as potassium, you can see they've got the same charge, meaning that their mass to charge ratio is going to be the same. So it will be very difficult for you to be able to separate these two ions, even if they are made of different substances, because they've got the same charge to mass to ion ratio. Let's consider question number 13. In an element, if an element consists of 37.50 atoms with a mass of 184.953 atomic mass unit, each and gives the 2.5% atom with a mass of 185.9560 atomic mass. What is the atomic mass of the element? Now, atomic mass, which I can say atomic mass unit, is given by mass 1 multiplied by its abundance plus mass 2 multiplied by its abundance also. So the first mass here is the mass. That is 184.953 multiplied by its abundance, that is 37.5. Now that's the percentage, so divide that by 100. And then plus you go to the next mass, which is 185.956 multiplied by its abundance, that is 62.5. Divide that by also 100. Okay, so just get to punch this on the calculator, whatever the mass that you get to find, that is the relative atomic mass of that element. Let's go to question number 14. Consider the following ions. These ions of oxygen, which are produced in a mass spectrometer. Which ion's path would be deflected most by a magnetic field? Justify your answer. So to see which one is going to be deflected the most, we need to find the mass to charge ratio. So for the first one, the mass to charge ratio, it has got a charge of 1, a mass of 16. 16 over 1, that is going to be 16. The next one, 17 over 1, the charge is 1, that is going to be 17. The next one, the mass is 16, the charge is 2. 16 over 2, that is going to give us what? 8. The next one, the mass is 17, so 17 over 2, that is going to give us 8.5. So to be deflected, the one with the highest mass is going to be little deflected. So the one which is going to be deflected the most is this one, because it has got a smaller mass to ion ratio. So this will be the first, followed by this one to be deflected, and then this one, and then the last one to be deflected is going to be that one. Okay, so the most deflected, when you're talking about the mass, the spectrometer, when the ions come like this, the one which will be more deflected like this is the first one I've labeled. And then the least to be deflected, just less, is the fourth one I've labeled there. Arrange the following in order of increasing ratio of charge to mass. So here it is ratio of charge to mass instead of mass to charge. E over m. So look at the charge is positive 1, the mass is 1. The mass is 12, so that will be 1 divided by 12, which is about 0.083. Then go to the next one, the charge is 2, the mass is 12. So that will be 2 divided by 12, which is 0.167. Go to the next one, the charge is 1, the mass is 13. That gives us 0.077. The next one, the charge is 2, the mass is 13. That gives us 0.15. Want to write in order of increasing ratio, increasing. So the smallest is this one, which is this one. This will be the first, followed by the first, which will be the second, and then followed by 1.5, which is this one, and then this one. So that will be the ratio. Question 16. Provide the systematic name of each of the following compounds. You have got this one. So this one is going to be called iodine. You have got 5 fluorines. So that will be pentafluoride. Iodine pentafluoride. And then if you look at this one, this ion, chlorine with 4 oxygens, is called a perchlorate ion. Now when you get to add hydrogen to a compound, make it an acid, right? So it is perchloric acid. That would be the name. If you go to the next one, this ion HCO3 minus is called hydrogen carbonate ion. also called bicarbonate ion. Therefore, the name of this one is going to be sodium hydrogen carbonate, which we can also say sodium bicarbonate, because hydrogen carbonate is also referred to as a bicarbonate, right? And then we go to the next one. We have got the OCl minus. What would be the name for the OCl minus? Just give me a moment. All right. So this ion OCl minus itself, the name is the hyperchlorite. This compound here, hyperchlorite. So we have got sodium in front, therefore the name is going to be sodium hyperchlorite. Actually, not hyper, but hypo, because we have got hypo means few. So that would be hypochlorite. That is the name. Sodium hypochlorite. Just the ion itself, that is the hypochlorite ion. Okay, this one. Now, when we get to look at this one, this is called phosphorus. We have got 5 oxygen pentaoxide. Okay, or phosphorus pentoxide. This one, we have got 6 fluorines. This is going to be referred to as sulfur hexafluoride. That is going to be the name, sulfur hexafluoride. And then the next question, provide the chemical formula of each of the following compounds. We have got cobalt 2 iodide. Cobalt, the symbol is C with a small o. We've been told it's cobalt 2 iodide. Okay, so if you have got iron 2, or let me say iron 3 oxide, this thing put here is the valence for iron, because these are transition elements. They've got different valences. So cobalt 2 iodide, it means it has got a valence of 2. Now iodine, we know that it's in group 7, meaning that it has got a valence of 1. So the 2 from the cobalt is going to come down here on the iodine. That will be cobalt 2 iodide. Then if we go to disulfurous pentasulfide, actually even this one would have said diphosphorus pentaoxide. Okay. Now the name which will be given to this compound is basically just phosphorus pentoxide. But we can say diphosphorus because we've got 2. Now diphosphorus pentaoxide, we are going to have phosphorus, 2 of them, and then pentasulfide. Sorry, that's sulfide. That is a sulfur with a 5. That's penta. All right, so that is it. And then I've got chloric acid. We can guess for this one what to be the symbol for chloric acid. So, what is it coming from? It is coming from chlorine. It is actually coming from a chlorine that is attached to an oxygen. Okay, the chloric acid. So what we have is that it comes from the chlorate ion, GCl3 minus. So, but because it's an acid, you get to put an hydrogen in the front. So it becomes like this. So that is chloric acid. So, and then D, we have got potassium permanganate. The permanganate ion is a manganese that is bonded, manganese with 4 oxygens like that. This is the permanganate ion. Now we're talking about it reacted with potassium, so just put a K in front, remove the charge. This is potassium permanganate. And then we're talking about strontium phosphide. So you can get to try it out. What do you think is going to be? So all you do is just you need to make sure that you know the chemical symbol for strontium, right? And that is S with a small r. And then you're talking about phosphide, that is coming from a phosphorus there. Phosphorus has got a valence of 3, so it's going to come here. The strontium has got a valence of 2, so it's going to come here. So that is going to be the chemical formula. And then you have got titanium 4 oxide. What do you think is going to be the formula? All right. So again, we need to know the symbol for titanium. Symbol for titanium, that is let me get just okay, that is Ti from the periodic table, that's titanium. And then we have got, it's going to have a valence of 4, okay. And then we have got oxygen. We know oxygen has got a valence of 2. This one they've told us the valence is 4 there. So we need to write it in the simplest form. So 2 can cancel here, 2 can cancel there. So that is going to be the symbol for this compound, titanium 4 oxide. And that marks the end of this tutorial. Thank you so much.